Okay, I think we'll get started. So today we're going to introduce a few ideas about acids and bases. We're actually going to redo something we've already talked about just to solidify those ideas. And this sets us up then to go back to those ice charts that we were just working on for acid-base reactions. All right, so we've talked about an electrolytic acid, which is an acid that breaks up into an H+. We talked about electrolytic base that breaks up into an OH- and then some other counterion. Well, we're going to expand the concept of an acid a little bit in what's called the Brønsted-Lowry definition of an acid. And here we consider an acid as anything that can donate a proton, and we consider a Brønsted base anything that can accept a proton. So certainly all of the electrolytic acids and bases are Brønsted acid and bases. So it's a broader set than that. But here's an example. Ammonia, NH3. NH3 is a gas, but a lot of it can go into a liquid. And when it goes into liquid, if you measure the pH, you'll get a basic pH. The reason for that is, and I think I'll just erase and give a spot here. This can react with water to give NH4 plus OH minus. And so it has raised the concentration of OH minus, so that's a base. We talked about that earlier. Anything that can, if the concentration of OH minus raises, then it's a base. And this did it not by producing OH minus directly, but by stealing one of the H's from the water and forming ammonium ion, and then the OH minus, and this is the results in a base then. So that's ammonia is an example of a Brønsted base and not an electrolytic base. All right, another set of definitions. If an acid gives up one, so if this is a Brønsted acid, donates a proton, one proton, then it's called a monoprotic acid. If it donates two protons, such as sulfuric acid, then it is called a polyprotic acid. Likewise, you can accept a proton that's a monoprotic base, and accepting more than one proton is a polyprotic base. So these are just some vocabulary words to pick up on. The other thing is the acid will always have a partner called a conjugate base. And likewise, a base will always have a conjugate acid. And they form pairs, conjugate acid-base pairs. And so let's look at this and see why this happens. So if we write an acid plus a base, and this acid gives, this acid donates the proton, because it's a Brønsted acid, donates a proton. The Brønsted base accepts it. Then we have these two species. Now, let's just write this reaction backwards. So that's all we're going to do here. If we went to the shelf and picked up this and this, put it in solution, the reaction would go backwards a little bit anyway. Maybe it really favors this way, but it's not going to go all the way. There'll be some equilibrium. And now this is acting as the acid, right? This is donating proton and this is accepting it. So the HA, the A is acting as a base in this reaction. And so if we look at this pair here, this HA minus pair, that's a conjugate acid-base pair. So we say that A minus is the conjugate base to HA. Likewise, let's see, I got this backwards. I'm going to try to be careful and write acid base. So now HB HB is acting as an acid here, it's a base here. And so the HB is the conjugate acid. It's the conjugate acid to B minus. Now, because we can always write the reaction one way or another, there isn't really anything special about being, say, the acid and the conjugate base. Those can be flip-flopped. But usually it's sort of obvious if we're putting a, say, like acetic acid into a solution, then we think of the acetic acid as the acid and then the acetate ion as the conjugate base. But certainly we could put acetate in solution. A little bit of that would form acetic acid, and then we could say that acetic acid is the conjugate base to the acetate. Okay. All right, polyprotic. Polyprotic, we have a series of equilibria here. We can lose the first proton, right, and pick up one proton, and then we can go further and lose the second one. And so we have a bunch of conjugate acid-base pairs here. So if this reaction goes backwards, then this is acting as a base for this part of the reaction. So the conjugate acid, the conjugate base to H2 plus is HA minus. Likewise, the conjugate acid to the base, here's the conjugate acid, that is HB minus here for this part of the reaction. So just think of this as a single monoprotic reaction. Then we think of this as a single monoprotic reaction. And so we have the acid-base pair here, this and this. So this is the conjugate base to this acid, even though here, this was the conjugate base to that. Right? So it's in the context of what part of this reaction we're talking about. And likewise over here. We can even have triprotic, so phosphoric acid, three equilibria, and a multiple amount of conjugate acid-base pairs. So that'd be a good exercise. See if you can write out phosphoric acid and identify all the conjugate acid-base pairs. All right, let's talk about water. We've mentioned this before, but we'll be a little more careful here now. So water auto-dissociates, and so that means it breaks up into OH minus and H plus, and that H plus always gloms onto a water. So we never have a bare proton just around in water. It's always H3O plus, or even higher H5O2 plus, and so on. So oftentimes we'll be talking about H3O plus, but from a bookkeeping perspective, if you work with H plus, you'll be just fine. Okay, so this has an equilibrium constant, a K, right? We call that K something special, KW. So K, this is KW for water. And now water, liquid, right? This is a liquid. This is aqueous. And so if we were to write the K for that, we don't put the water, right? That's a pure substance. So it really is sitting under here as a 1, but we don't write it because we take that to be 1. All right, so let's write the ice chart for this. I won't write the water column, although you could, and just put dashes there that's not involved. So we have ICE, 0 amount starting. So we're going to start with pure water, intact water. And then water in water dissociates a little bit. So a little bit of X here, and a little bit of X here. And so both are positive X here. And then we write then our KW equals X times X, or X squared. And so X is just the square root of 1 times 10 to the minus 14. So that's 1 times 10 to the minus 7. And so in water, the concentration of H plus equals the concentration of OH minus, and that concentration is 1 times 10 to the minus 7. So if we take minus the log of that, we get pH of 7. So that's where we get the pH of 7. Now, it's sort of a teeter-totter effect here. If we add a Brønsted acid, then the amount of OH minus will go up, and it will do so by consuming or reacting with the OH minus, and that will go down, such that the product is equal to Kw. And so so if we add acid, H plus goes up, OH minus goes down. And they're sort of stuck together. If we add base, then H plus goes down, OH minus goes up, and they're stuck together via this water dissociation constant, Kw. All right, let's take negative log of Kw. That's what's going on here. And so let's think about pH here. We're going to take negative log of Kw. So that's going to be minus log of the numerical value of Kw, 10 to the minus 14. But Kw is always going to be this times this. So that's going to be concentration of H plus and OH minus. So negative log of this is 14. So there we get 14. And then by properties of logs, we can split that product into a sum. There's a minus sign out front. And then this is pH and this is POH. And so here we get this expression that we had talked about earlier. And it gives us our pH scale. Our pH scale ranges from 0 to 14. And it doesn't really make sense to talk about a pH of less than 14 or less than 0 or greater than 14. Although we can talk about stronger relative acid strength, not related necessarily to that. Okay, so let's just finish with some examples. We're going to just finish with strong acids and strong bases. So we've done this before. This is kind of a repeat. If we have a strong acid or a strong base, that means it fully dissociates. We don't need an equilibrium constant. We're saying the equilibrium is so far over that our equilibrium constant is essentially infinity. So we say this breaks up completely. So if I make up a 2.3 molar solution of HCl, then that means I have 2.3 times 10 to the minus 3 molar of OH of H3O plus, which gives me a pH of 2.6. Now, actually, let's do this. So then the POH is going to be 14 minus 2.63. So that is going to be equal to 11. Let's see, I think it's 11.36. Okay. And so that means, well, so we take the OH concentration is 10 to the minus 11.36, okay, whatever that works out to be. And the H plus concentration is 2.3 times 10 to the 3. Okay. Let's just do the reverse here. Let's make up a similar solution of NaOH. So now we should expect a basic pH. We can directly calculate the POH. We get that. And so then our pH is 14 minus 2.63, which is 11.6, basic solution. The last one's is kind of a trick question. We talked about this earlier. What about a pH of 2.63 times 10 to the minus 8 molar HCl? Well, if you take the negative log of that, you're going to get a number bigger than 7. And you say, well, we added HCl and got a basic solution. Well, that can't be right? Well, we know now, and we talked about it before, but we know now here with the ice chart that the concentration of the concentration of H plus from water is 1 times 10 to the minus 7, which is bigger than 2.3 times 10 to the minus 8. And so we have roughly 1.236 times 10 to the minus 7 molar. And we take the log of that, negative log of that, and we get 6.91, which is acidic. So we've added a little bit more acid than what's there through the auto dissociation, and that's dropped our pH a little bit to 6.9. All right, so this is just some definitional stuff. Read this section of the book. Not a ton of problems, homework problems on this. Really internalize the idea of conjugate acid-base pairs. This should be pretty much a breeze for you, especially now knowing to be careful for this situation. And so we're going to move now to the case of weak acids and weak bases. So they don't fully dissociate. Now we combine that with the ice charts, and we can figure out how much they do dissociate and calculate a final pH. So that's what we'll be doing.